All right, in this video, this is video number 11 in the respiratory system series, and we're continuing on from the last time where we were going through the hemoglobin dissociation curve. And so again, if you look at the hemoglobin dissociation curve one more time, at the lungs, if you look at this, at the lungs, a large drop in PO2 leads to a what? Drop in hemoglobin saturation. And again, we're not really defining what do we mean by large, but again, the shape of this, it kind of flattens out before it takes this huge dip. What I would say to you is that a large drop in PO2 leads to a small or moderate drop in hemoglobin saturation. But once you get to the tissues, look what's happening here. At the tissues, a large drop in PO2, let's say you go from 40 down to 20 or something, that's going to lead to, because it's a hugely steep drop off, that's going to lead to a major, significant, meaningful, large drop in hemoglobin saturation. Okay, so that's just the shape of the curve. This slide over here, it's got stuff printed out for you. Again, hemoglobin is almost 100% saturated in systemic arterial blood. No O2 has been unloaded to the tissues. Once we get to the tissues itself, the PO2 of the tissues is about 40, and in resting state, resting tissue, the hemoglobin unloads only about 25% of its oxygen. Therefore, in the veins, you still have 75% saturation. Okay, that's what we had talked about before. But now what I want you to see is, let's go back to this slide here. See how it says tissues less than 40? So what ends up happening, kind of the standard number that we use is the resting tissue has a PO2 of 40, but then let's say the tissue, let's say you're exercising, let's say the tissue happens to be the quadriceps, and now you're running or you're doing squats or whatever it is, you're doing something, and when that happens, of course, the overall metabolic rate is going to increase in those tissues. There's going to be a greater demand for ATP, therefore there's going to be a greater consumption of oxygen, and therefore the PO2 is going to drop in that tissues because I'm chugging oxygen now. Instead of sipping on oxygen to maintain myself, I'm chugging oxygen. So when that happens, what are we seeing? The PO2 of the tissues, let's say it's going to go from 40 down to whatever this is. Let's call this 18. What do we see now? Now we see that, whoa, I'm going to unload a ton of oxygen. Hemoglobin will unload a ton of oxygen. Hemoglobin saturation is there, looking at about 22% now. So here, if you read this out, point C, when a person exercises vigorously, hemoglobin unloads most of its oxygen in the tissues. In such cases, hemoglobin entering the venous blood is only 25% saturated. So meaning that when we go here, remember that this is venous blood, you still have 75% saturation at rest. But if I'm exercising, man, I'm going to unload not all, but most of this hemoglobin where I only have 20% saturation left. That will be venous blood in an exercising state. So, again, I guess what I want to reiterate here is that there's no feedback loop. There is no intelligence. There's no benevolence. This is simply the property of hemoglobin and hemoglobin's affinity for oxygen at a given PO2. So now you know what dissociation means. What does affinity mean, since I've used that word officially now? Affinity simply means attraction. Hemoglobin's attraction for oxygen. So here at a PO2 of 100, we say that hemoglobin has a high affinity, a high attraction for oxygen. Here at an exercising tissue, hemoglobin is going to have a lower affinity for oxygen. So the affinity for, hemoglobin's affinity for oxygen is much lower as PO2 gets lower. All right, so now let's talk about shifting this curve. You know what this curve looks like now, and I want to show you a picture where this curve can shift to the right or left. And imagine this curve here, we take the thing and we just shift it over to the right, and meaning the right, meaning this direction. This right here, this arrow would indicate a shift in the curve to the right, whereas if I went the other way, if I took this and I shifted it to the left, that would indicate what I mean by shifting the curve to the left. Maintaining the shape of it, just kind of dragging it over. And so let's look at this. What this is showing you this kind of, whatever color this is, 37 degrees Celsius. This is your normal body temperature. And what we see here is 43 degrees Celsius and 20 degrees Celsius. So obviously hotter and colder. And so let's use some language to describe the movement of these curves. This orange curve in 43 degrees Celsius, how would we describe that with respect to the normal body temperature line? Would we say this curve is shifted to the right, or would we say it's shifted to the left? And what I would argue is I would say that this, whoops, let me drag that back. What I would say is that this curve has shifted to the right. And again, we could say at every point, this thing has shifted way over, not way over, but it's shifted over to the right. And so, yep, we're going to say at warmer temperatures, the hemoglobin dissociation curve shifts to the right. Okay, so there's your answer. At colder temperatures, what happens? At colder temperatures, we would simply say the hemoglobin dissociation curve then shifts over to the left. And we could continue to draw some of these arrows out. At colder temperatures, the entire curve shifts to the left. Well, so now, okay, you got that now. At warmer temperature shifts to the right, colder temperature shifts to the left. What does that mean? Okay. In order to understand what that means and how to interpret that, let's just pick something. Let's just pick a 60, a PO2 of 60, all right? Now, what is the hemoglobin saturation normally when you have a PO2 of 60? It looks like it's going to fall right at about 90% saturation. Now, when I actually shift the curve over to the right, what happens at a PO2 of 60? So the same PO2, what happens? My hemoglobin saturation is now, whatever that is, 78. So what just happened here? I'm saying to you, at a given PO2, the hemoglobin saturation is lower at hotter temperatures, at warmer temperatures. Let me say it differently. At a given PO2, the affinity for hemoglobin's affinity for oxygen has decreased. Meaning, instead of holding on to 90%, I'm only going to hold on to 78%. Let's see if that's true at other areas. Let's go down to tissue, normal tissue. So let's go normal, healthy tissue at 37 degrees Celsius. What is hemoglobin saturation? It's 75%. Well, if I heat up the tissue, if I warm up the tissue, what do we see now? Hemoglobin saturation is now about 55%. So really, I'm offloading more hemoglobin at warmer temperatures. And at colder temperatures, I'm offloading less oxygen. Did I say offloading hemoglobin? Oh my gosh. My head is spinning. At warmer temperatures, my hemoglobin is offloading more oxygen. Okay, right over here, as you can see, because it's got a lower hemoglobin saturation, because the affinity, hemoglobin's affinity for oxygen has decreased. Let's make this make sense. Look, at warmer temperatures, what happens to overall metabolic rate? Overall metabolic rate goes up. You know this from a general chemistry course or Bio 101 or first semester of A&P, where you've learned that as you heat things up, the rate of chemical reactions will increase. You've learned that already. And so that is true in physiology as well. That's why we give ourselves a fever when we have an infection, because we need to increase metabolic rate of immune cells. So what we're seeing then is that as tissues have warmed, they're going to increase their metabolic rate. Now, this can go one of both ways. Either you're warm and therefore things are moving faster, more chemistry is happening, or you're doing more chemistry, right, because you're exercising and therefore your tissue is warming up. Regardless, at warmer temperatures, hemoglobin more readily gives up oxygen. This is what it means to shift the curve to the right. Now, shifting the curve to the left, what happens when things cool down? Metabolic rate slows down. Therefore, there's a less of a requirement for oxygen. Therefore, hemoglobin's affinity for oxygen will increase. In other words, I'm going to hold on at a given PO2, let's just do 30. At a given PO2, instead of having 55% saturation, I now have about 90% saturation, because hemoglobin's affinity for oxygen has increased. Okay, that's the effective body temperature. In any case, I hope you make that make sense, meaning that when temperature increases, metabolic rate increases, there's a higher demand for oxygen. So this design for hemoglobin just makes sense. Let's look at pH. When you look at pH, what we're looking at here is that normal blood pH is 7.4. At 7.2, we're more acidic. So what you'll see is that as acidity increases, what happens to hemoglobin saturation? As your acidity increases, as you get more acidic at 7.2, your hemoglobin affinity decreases, hemoglobin saturation decreases. Okay, that's what we're seeing. We're more readily giving up oxygen. Now that in and of itself might not make a lot of sense, but what we'll see eventually, we'll see how carbon dioxide levels directly relate to acidity levels, and when we see that, this pH thing might make more sense. But what you want to know is that as you get more acidic, the hemoglobin dissociation curve shifts to the right. As it shifts to the right, hemoglobin's affinity for oxygen decreases. As pH becomes less acidic, as it becomes more alkaline, the curve shifts to the left. When it shifts to the left, hemoglobin's affinity for oxygen will increase, meaning that you'll give up less oxygen at a given PO2. All right. The next one then is carbon dioxide. If you look at this, as carbon dioxide levels increase, 80 millimeters of mercury, PCO2, as carbon dioxide increases, your affinity for oxygen, hemoglobin's affinity for oxygen will decrease. The curve shifts to the right. And as PCO2 decreases, the curve will shift to the left, increasing hemoglobin's affinity for oxygen. The last one here that I want to show you is 2,3-DPG. So 2,3-DPG, let's say we have normal 2,3-DPG. What is that? Is 2,3-diphosphoglycerate. Diphosphoglycerate. That's what 2,3-DPG is. And what this is, it's a glycolytic intermediate. Now this is showing you experimentally when people add or there's no 2,3-DPG. But 2,3-DPG is a normally occurring metabolite as part of glycolysis. So let's make this make sense. When you have 2,3-DPG, 2,3-DPG levels are going up, let's say, and that would be the situation of this added 2,3-DPG. Why is that happening? Well, you're seeing more and more 2,3-DPG because you're running more and more glycolysis. Well, if I'm running more and more glycolysis, presumably I'm doing that because I have a greater need for oxygen, and meaning that I'm probably going to do much more citric acid cycle, much more electron transport chain, right? If you remember these metabolic pathways. So what I want you to see then is that the curve will shift to the right. The curve shifts to the right so that I'm offloading more oxygen to tissues in the presence of 2,3-DPG. Okay, and that should make more sense because there's greater demand for oxygen. All right. To recap then, we've looked at the hemoglobin dissociation curve. We're recapping lectures 10 and 11 now. We've described the hemoglobin dissociation curve, the overall shape of that curve and the significance of that shape. And you can see what you can do as a thought experiment is say, hey, let's say the shape wasn't like that, but the shape was more like this as a straight line. If the curve was more like a straight line, then what we're seeing is that a small drop in PO2 leads to a small drop in hemoglobin saturation. A major drop, there's a linearity to that, right? But because we have this kind of sigmoid shaped curve, it's got some unique properties at the upper end as well as the middle end. Okay. Anyway, we talked about shifting the curve to the right and what that does for hemoglobin affinity. If you shift the curve to the right, that means you are decreasing affinity of hemoglobin for oxygen. If you shift the curve to the left, you are then increasing affinity of hemoglobin for oxygen. And what is the effect of each of these? Warmer temperatures will shift the curve to the right. More acidic pH will shift the curve to the right. Increased 2,3-DPG will shift the curve to the right. Okay, and that'll wrap it up for the hemoglobin dissociation curve.